DNA provides the instructions for building which type of biomolecule. I think it's pretty clear that it's RNA.
What? I thought it was protein.
If you read this, I think it's clear it's RNA. Shush, please. Thank you. It's DNA gets transcribed into RNA. That's what you're dealing with here. This part of protein synthesis is transcriptions. Now, as I said last week, the central dogma of biochemistry is that you have one gene, one enzyme. But as per the multiple examples I gave you last week, not every gene makes an enzyme, a protein. Not every gene makes a protein. If you did module 2, you know that. If you're on your phone, I'm taking it away. So just give it here. Give it to me. I'll turn it into the office. Or you can just walk into the office yourself. I don't let them know you're coming.
Okay.
All right, go take the pass. Go give them the office. Tell them you had the phone out in an appropriate time. They will keep it the rest of the day. Go ahead.
Okay.
Thank you. And if you don't make it there, it's going to be a suspension. I'm writing a referral. All right, thank you. And I'm recording it too. It's one minute and 30 seconds into the answers to the test. You are on your phone texting or whatever. Okay, very good. So our DNA gets turned into RNA. Not every gene gets turned into a protein. Where is DNA located in a eukaryotic cell? I think it's in a eukaryotic cell. It's going to be DNA's in the nucleus. I think that's simple. In a prokaryotic cell, it's in the cytoplasm. It has no choice. There is no nucleus in the cytoplasm in a prokaryote.
Is the cytoplasm also like the nucleated region?
There's a nucleoid region, you could call it. It's a region, it's just a space in the it's like the middle of the room.
Oh, okay. I got a nucleated.
It's not really a difference. It's not a chamber. There's no walls, no membranes. All right, going on. Which cellular structures are the machines that build proteins? I hope you put ribosomes.
I put either attached to here or on the cytoplasm.
That's correct.
And the rough cytoplasm.
RER
Yeah, the rough one.
or cytoplasm.
The rough yeah.
And the rough ER is in the cytoplasm, but cytoplasm free floating. If you want to be specific. If the DNA can't leave the nucleus, how do you think the DNA instructions get to the ribosome?
It gets copied.
I think we went over it fairly straightforwardly last week, repeatedly. And yet some people still are going to get it wrong because they're not listening to me now, even though they should be the ones explaining this.
It gets copied into the RNA.
It gets turned into RNAs, correct. DNA gets turned into double-stranded, long DNA gets turned into short,
And it leaves the
much shorter single-stranded RNA. And specifically, a type of RNA called mRNA. If it has the message leaving this nucleus, it's mRNA.
It goes to the nuclear pores, right?
It goes to the nuclear pores. In fact, you have the drawing right there. There's a pore. It goes through. This is RNA. There's a reason they say RNA, because transcription takes DNA and makes RNA. It doesn't always make mRNA.
It makes
Sometimes it makes other kinds of RNA. But when we're dealing with transcription, we're talking about taking DNA and making the RNA. Now RNA can leave. If it's leaving with the message, then it's mRNA. All right. So then here, module 2 says flow of information. It tells you most of the answers right here in the POGIL. Most POGILs do. Figure shows the information from DNA to a molecule called RNA in the nucleus, and then the creation of proteins. We now know that RNA, which is similar to, but not identical to DNA, moves from the nucleus to the cytoplasm. RNA is a nucleic acid polymer composed of nucleotides like DNA. However, RNA has a sugar ribose instead of deoxyribose, and a nitrogen-based uracil instead of T. U instead of T. We've known that. You know that.
Yeah.
Instead of DNA, it's deoxyribose and thymine. Deoxyribose is the sugar. You see, deoxyribose.
It's double stranded.
And in DNA, and it's in RNA, it's ribose. In DNA, it's thymine. In RNA, it's uracil. So that's how they match up. Also, RNA is much smaller molecule, obviously, a much smaller molecule. Since DNA is billions and billions of nucleotides long, it's something like meters long. RNA is really tiny compared to that. Right? It's only a small piece of a gene. It's only a gene, which is a small section of that long chromosome. And on top of that, and you saw a video of that chromosome, how big and complicated and convoluted it is. And when you look at a small gene of it, a small section of it, even that is sliced up and made smaller to make an RNA molecule, so an mRNA molecule. So these are much smaller than DNA. So DNA gets turned into RNA. I think that's simple.
And then it turns into protein.
And then the proteins. I really don't see anything hard there. Transcription is pretty easy. Translation is a little more complicated.
It was harder.
It's not that much harder, but it's just a little more complicated.
It was more.
List at least 3 different differences in DNA RNA. Well, that's easy.
DNA has ATG.
Ribose, right? Versus deoxy, ribose.
And then one has ATGC, one has ATG.
Let's just put T versus U, right? Single-stranded, that's right.
And then double-stranded.
Versus double, right? Those are at least, Then the function, you can look at the function. DNA is just holding the information. RNA is actually doing stuff with that information. Like, we could talk a lot about the different things between differences between RNA and DNA. RNA is actually much, much more active, many different versions of it, doing a lot of different things. But DNA holds all the information. Think of an emperor. Isn't really doing much, but he has armies and generals and captains and lieutenants all running around doing all kinds of things.
I have a question for you.
All right, so by tomorrow, I need you guys to be able to explain all that plus the rest of it in Module 2. Good luck. And then 3, don't forget 3. Now, translation, I just said it again, but I'm gonna say it. I'm going to keep saying it, so hopefully it sinks in. Hopefully at some point you're going to say, let me just pay attention one time. And what you're going to have is there's a cell, there's a nucleus. Here is DNA, and that's where DNA is and will always be. If there's a nucleus, DNA's in it. That's what it's for, holding DNA, protecting it. The holding and protecting the message that you inherited from your parents, who inherited from their parents, etc., etc. So DNA to RNA is what happens in the nucleus. And if you read and think about it, and if you listened last week, then you know why DNA to RNA happens in the nucleus. I think this is too big. Yeah, way too big. So DNA to RNA, oh my goodness. DNA to RNA is happening in the nucleus. In the cytoplasm, there's 2 places. Out here, you're going from RNA to protein.
That's translation?
This is what we call translation. Translation here is based on a codon sequence. So you have this mRNA, If you've done this, you paid attention last week, you know what that is. The mRNA is red in threes. So that's why it's called a triplet code. Every three. 1, 2, 3. 1, 2, 3. Every three, starting at AUG. It all starts at AUG. When you get to the first AUG starts the process. And from then on, it's every three. 1, 2, 3, codon. 1, 2, 3, codon. Why weren't these three were not codons? The first codon starts with AUG. This is called the start. And it keeps going forward. 1, 2, 3. 1, 2, 3. Every three is called a codon.
Wait, so AUG is an example of codon? AUG is 3 letters? Yeah.
That's correct. So there's 4 letters, correct? A, U, G, and C. No T. AUGC. 4 letters. When the ribosome, I guess the other part of this, when the ribosome, the enzyme, which is made of RNA, first comes along and reads AUG, boom, it starts the process. It starts the process. That AUG is called the start codon. That's where the codons start. Am I clear on that?
Yeah.
That's it. And it's going to keep reading until it gets to this amazing. It's really complicated. It's a really complicated term, so you might want to write this down. So the codon that's called, this is, wow, I don't know why they make it this hard. Stop codon. Yeah. It was a joke. So it goes from the start codon and it continues until it reaches the stop codon. Every 3 along the line. Is that clear? It really is simple.
Wait, so the stop codon is mRNA?
It's all in the mRNA. It's a chain. Remember, RNA is what? A chain of amino acids. A chain of nucleotides, of RNA nucleotides. I'm going to draw it again. I keep drawing it. You built a DNA molecule, correct? You know what the nucleotides look like.
RNA is chain of...
This RNA is a chain of RNA nucleotides, just like the DNA that you built last week during your lab. It doesn't matter to me. That we built. Yeah. Is it what? That is not a bad question. That's being used. It's used in a different way. What you're talking about is used in a different way. So you have this nucleotide, this nitrogenous base, this ribose. This is ribose now because this is RNA. And up here sticks another carbon that has a phosphate. You saw that. You should know that. That noise is on record. And this is just another example of the childish behavior. So when your parents come in here and ask me, why is my kid suspended? Why is my kid not have a good grade? Why are they put outside a room with a book? I'm going to say, look, they're making pig noises in the middle class. And then laughing about it.
This still in translation, right?
Yes, but when you have RNA, if they're kind of a straight chain, where you get. All right. So, no, the sequence the sequence of nucleotides. If you have AU, GG, AU, whatever, right? If the sequence is such that the message is straightforward, is kind of, we have what's called a messenger RNA, mRNA. It's just could someone close that door? Where AUG is the beginning and you're reading 3 codons after that. It's just pretty much just a long RNA molecule, a wiggly line. Is that clear? Remember, this is a nucleotide, one nucleotide connected with a sugar phosphate backbone, one after another after another. So this is not a tape like we draw out a single line, but really it's frozen. Hold on. So there's three nucleotides. Just stick off this end here. They're called anticodons. In the activity, you see them drawn. They're drawn for you in the activity. You flip through the pages. In your chapter reading, they describe them as well. So it's just all tRNA is RNA that's folded. Is that clear? Folded in this way. Look at the way I'm drawing. In general, this is sketch. It's folded in this way. It kind of looks almost like a weird T. And has 3 little nucleotides that stick off to the side. Yeah.
So tRNA is mRNA that's folded?
No. This is all just RNA. All of them are RNA. RNA that's not folded, has a message, we call it mRNA, messenger RNA. mRNA, it's just that simple. RNA that is folded because of hydrogen bonding between the nucleotides, we call it tRNA. And what they do is they carry an amino acid. Remember, there are 20 amino acids. AA, anywhere from 1 to 20. There's 20 different amino acids. There's many different tRNAs that carry 20 amino acids. But they're very specific. So for instance, if these 3 anticodons were A, U, and G, AUG, the start codon, then they would carry the amino acid methionine. Because I've been doing this 25 years. Also, I can read the chart that I'm about to show you that you have in your packet. And also, I told you last week. So AUG if the anticodon, the 3 at the bottom say AUG, then it's carrying methionine. That's called the start codon. That's where it's going to always start. They're always going to start with methionine. AUG. So the tRNA bends and twists, and it carries amino acids from the cytoplasm over to the ribosome. There's millions of these in the cytoplasm, just kind of floating around, waiting for a ribosome, waiting to find a ribosome. Then there's another kind of RNA called rRNA. Actually, rRNA has two different kinds. There's a small and a large. And what will happen is that the big one will fold and look something like this. And actually, let me redraw that. It'll look something like that. It looks so. It's a horrible drawing, but they draw it pretty well in the Pojo, and in the book they have computer drawings for you. So the ribosomes. You're looking at ribosomes. So there's many different ways to draw it. I like to draw it to make sure that you see that there's 3 places, there's 3 spots. Why 3?
Because it's 3.
That's right, it's reading 3 at a time. Why are we reading 3 at a time? Because the enzyme, the ribosome, by the way, rRNA, R stands for ribosome. Ribosome has 3 slots. That's why it's triplet, because when the mRNA sits in the middle of it here, as the mRNA sits in the middle, I think I drew it in blue. Let me draw it in blue. So mRNA sits in the middle. It's going to read the first one, the second one, and the third one. And then on the other side, as the tRNA comes in, the tRNA is going to read the anticodon. So the tRNA has this triplet embedded here. We call anticodon. It's going to match. So if this is AUG, then the anticodon is going to be UAC. The anticodon, so this, for AUG, the thing that's going to match AUG is going to be UAC. And UAC is going to carry methionine. So this would be methionine. Hold on a second. This here would be methionine if it's UAC, right? The good news is you don't have to know this. You don't have to know the anticodon. You only have to read the codon. If you know the codon, you know that it's going to be matched with the methionine. Every tRNA is very specific to that amino acid. The UAC will never carry anything other than methionine. That's the only thing that UAC is going to carry. Is that clear?
Yeah, it's good over.
AUC is the amino acid you said, or the methionine?
AUC is RNA. It matches the AUG that's on the mRNA. mRNA is here in blue, and the tRNA is in white. Do you see it? They're both RNA. But this tRNA is carrying an amino acid.
Also, the
MAT is the amino acid, correct. MAT is the amino acid, and the tRNA, it's made of RNA, that's why it's called that, it's also, if you want a name that makes sense, it's actually called transfer RNA. Why is it called transfer RNA? Because it's the RNA that's transferring the amino acid to the ribosome. All right. So that's going to continue. The ribosome is going to ratchet its way downstream. This mRNA is long. It might be 100 to 5,000, whatever. I don't know. I'm just making those numbers up. 100 or 1,000. I don't know. Nucleotides long, and it's going to read them. It's going to read them 3 at a time, and it's going to put together, every time it has 3, it's going to bring another amino acid until it gets to a stop codon. So this is going to stop it, everything falls off, and you've made your protein. Remember, at the other end, you're going to have your protein. One amino acid linked to another amino acid, linked to another amino acid, covalently bonded through peptide bonds, as we've been discussing all year long. Just amino acid after amino acid after amino acid, all the way down the chain. So we take this long list of RNA that we copied from DNA. We copied it from DNA, we changed it, we spliced it, we cut it up, we put it all back together. Then we ran it through a ribosome, and for every 3 RNAs, I get 1 amino acid. Boom, 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 boom. That's why you need so many nucleotides, because every 3 gives you 1 amino acid. And some of these amino acids, a few hundred amino acids, some of these proteins are a few hundred amino acid long, right? If you have 100 amino acids, that means you have to have 300 at least, right? Nucleotides. So you have 3 times as much. All right, so let's go back. Let's go back to the document. So you'll be able to draw on this board. You can use a Google slide if you want, but I need to see you draw it out, whatever it is. I don't need you can put a Google slide up there, but you need to be able to draw. You need to explain it.
The whiteboard?
Yeah, I would use a whiteboard. You can use my iPad, whatever you want to do. All right. I will use the whiteboard though; it's more interactive for you guys. It keeps everybody going. So let's take a look. You get an mRNA strand, and the first step is AUG. It reads AUG. Let's look and see if we can read it here. A is the first one here. Why? How do I know? Because that's the first base. U is the second base here, and G is the third base here. But Mr. Mendoza, there's 1, 2, 3, 4. How do you know which one it is? Well, you look at the first one, you say A, A-U-G. So the first, you go with this row. So the answer is somewhere in this row. Does that make sense? So it's A. Now U is the second letter, so that has to be somewhere in this column. Does that make sense? So A-U, so somewhere where this column meets that row. Is everybody good with that? And then lastly, you're going to find the third base, G, which is in that column, and you can call it all the way across to this column here, and what you get is AUG, methionine, MET. Now, let's go ahead and take a look at, let's pick another one. Let's pick what happens if I get the next, after AUG, got methionine, what's the next amino? So right now, if I were going to make a polypeptide, if I were going to write the polypeptide, methionine, I don't know what that conversation is about upperclassmen, but I can hear you all the way up here. So methionine is the first one, and it's connected to the next one. So what if the next one's on the mRNA said CCU? Well, we would find C, there's a second base, and then U. So somewhere around here in this block, and there it is, right? CCU is what? Proline. So it goes proline, and then et cetera. Let's say it gets AAU. What's AAU? AAU is what now? A, somewhere in this box. AAU, U is here, and somewhere in this row, in this box is ASN. ASN, I think, if I don't remember, I can't remember what ASN is, to be honest. LYS is lysine, ASP is asparagine, proline, leucine, valine, isoleucine, tryptophan. I can't remember at this moment.
Another one, just say some random letters so I can do it.
Well, what if the next message on the mRNA is UGA?
It's what?
UGA. U?
UGA stop.
G?
UGA
Then would it be
stop.
right here?
Yeah, what is it? What's the amino acid?
Stop.
Stop. There is none. Stop means stop. It's over. All right, so it's not that hard, right? It really isn't. But it's the problem is, how do you explain it? And also the problem is, if you're not paying attention, you don't understand it. Hold on, give me a second. Let me answer the phone.